So we're just getting ourselves back into random networks so we can build on this. Degree distributions, right, beautiful thing. Okay, so this is, so I guess I started this by saying that n and m, right, the number of nodes and the number of edges, hugely important things, got to set them up. And then the next big part is really the degree distribution, which, if you had a temporal dynamic network, would be a contact rate type thing, various permutations of this, but degree distribution, we're thinking about static networks. All right, so how do we build this, right? So we're going to choose that method, that first method for constructing networks. So one node has n-1 choose k. That's how many ways you can choose k other friends. And each of those connections, you'd have to turn them on with probably p, and all of the other ones would have to fail with probably 1 minus p. And so we can put it together like this. We have a binomial distribution. So probably thinking about one node, and therefore all nodes, probably that a node has a degree k, given that we're in a network of size n, and there's a connection probably of p. So there are n-1 other friends that a node has, potentially. We want to choose k of them. So that's how many different arrangements we can have. So this is counting. And then for each one of those, we have to have this happen. We have to have the k of them be, the coins we flip, they have to switch on, and the coins we flip for the others have to turn off. And the others, there are n-1 total friends minus k, right? These things add up to. Okay. All right, so it's a binomial distribution. And then you can mess with this, right? And look at the limit as n goes to infinity, and the piece we'll need to do in here is to replace p here by the right thing, which is average degree divided by n-1. Right? Let me write that down. Where's my thing? Right, so this is just a crucial thing. So we had average, also sad, I lost it. Yeah, average degree is also p n-1 in this construction method, so we can replace p with this. Okay. Right, and we're going to fix this. We want to say, average degree is 7, and then look at the limit as n goes to infinity. And if you do that, you get a, right, you'd think you'd end up with a normal distribution because this is sort of what happens a lot, but that's not the right game. So this is what I've been saying. So it's roughly going as p times n. And if you do this limit, okay, so this is what we had before. This is going to, and we're right. So this is from the factorial at the front. This is the classic, 1 plus blob divided by n to the n. That ends up as scaling as e to the blob, right? Which you can always reassure yourself with L'Hopital's rule. It's very nice. And this object here, right, so this is our average. The notation is not ideal. Sometimes people use just a completely different thing here like z, but this is the average degree, these are constants. And this is a Poisson distribution, right? Which is the right kind of thing, right? It's a distribution of a discrete variable, 0, 1, 2, 3. It's a fine distribution. It's been used for lots of things, right? Things like, right, so it's about how many things happen in a given time period, given a rate of occurrence, right? And things are, otherwise random. And it does pretty well for some strange things. Okay, yeah. So actuarial people have been quite fond of this for a long time. But it appears here very naturally. It's a quite well-constrained distribution, as it dies away fast. There's no heavy tail or anything like this. I mean, the point is that for random networks, you have sort of a typical number of friends, and there's some variation around it. But that variation is quite small, and we'll get to this. But the variance for a Poisson is the same as the mean, right? Which is just a nice thing. So it means that the standard deviation is the square root of the mean. And so that means you've got something like, so say we've got some, our Poisson is out here, then the typical width of this thing, so this is this is our mu, the typical width of this thing, 2 sigma, is square root of mu. So, you know, from a long way away, this starts to look pretty much like a spike. Right? There's not a lot of room around the thing. Okay, so this is the point, this is the variance. You can go through and compute it. So it's not shown here, but the second moment turns out to be the first moment squared plus the first moment. And then if we compute the variance, we get this result here, right? So that the variance is actually the first moment. So that's kind of a nice thing. And it leads to some odd things in the way people have understood how spreading works, because there's a very peculiar property of the Poisson distribution. We'll get to that again. Anyway, that's a good thing to remember.